So we're here to discuss sort of theoretical physics and machine learning, right? So theoretical physics is a pretty what is MapD? MapD is an extreme analytics platform with a GPU-powered SQL engine, and so you can ingest data into MapD using the different connectors like S3, Kafka, JDBC, and bring it into MapD core, which is a columnar database. And so what you have is a columnar database that is built ground up with making use of the infinite parallelism that is with GPUs, and there's a number of optimizations that we do. So you have the core, which is the database, and then we have the immerse, which is the UI. And so how do we, what the main intent of MapD was to, when you have a lot of data and you want to analyze it visually in real time. And so when you're talking about data sets, we're talking about billion row data sets. And the way we achieved is we have optimized a lot of the SQL operations. For example, filtering, which uses the where operation, or segmentation, which uses the group by operation. So these have been optimized, and we use a technique called just-in-time compilation. So we use the LLVM approach, where we create an intermediate code, and then depending on the backend, whether it's an GPU or x64 or an ARM, we create the final code. And this allows us to run on multiple platforms, but of course on GPU we have extremely great performance. And we also try our best to keep the data as much as possible in the GPU memory, and we also try to vectorize most of the SQL query execution, and so that way it can leverage the GPU platform. Now on MapD Immerse, which is our visual front end, it makes use of the backend MapD core database. We support very complex charts like point map, scatter plots, and also GIS representations. At the same time, we also support standard charts like bar chart, line charts, and IMAP. And the way we do it, the simple ones are rendered on the front end on the browser using D3. For the back end, we leverage the back end GPU to make use of the graphics pipeline. So we do the rendering, and then we create a rasterized image, which is then sent to the client. So that way, we're just sending the PNG files for all the complex rendering. Now, it'll all become very clear when I talk about a lot of data at extremely fast pace by doing a very quick demo. I know this is a very short talk, so you can also go and try this. You can go to mapd.com/demos, and we have a number of demos here with very large data sets that are hosted on our website, and they're all running on GPUs. So I picked the taxi demo. This is like one of the smaller ones. It just has about 1 billion rows, and so we have the point map, which shows the different locations, and then you have the different payment types as a bar chart. So that's a simple one. And then you have the line map. Now, I'm going to click on credit, which shows how many people use the credit payment, and you'll notice that all the charts got filtered at the same time. So the SQL operation was applied across all the charts. And when you have a mix of all these complex and simple charts together on a single dashboard, it really gives you real insights into a lot of data. And there is no pre-aggregation or pre-indexing of data. This is raw data. You can even go and add a filter, like select the database and say, hey, I want to find out who are the folks who are using credit versus cash. Is it happening more than the amount is greater than 20? So as you can see, the global filter gets applied to all the different charts. So now, this is all achieved by keeping most of the data in GPU memory, and as you have an orders of magnitude faster. So I'm going to now hand it over to Vamsi, who's going to talk about how we make use of this in our machine learning pipeline.
Hello, good morning, everyone. So, as Veda mentioned, I'm a data scientist at MapD. So the traditional machine learning pipeline, as you can see, one on the leftmost corner is like going through Spark, and then pre-processing your data through Python and doing machine learnings on CPU, and then GPUs came across, and we started doing it on GPUs. Like MapD, as it is mentioned, it's a GPU database hosted on GPUs, and then with Python machine learning. But the problem with the second one is like we have to go copy the data to the host memory in order to do something. When I say host, I mention the CPU, and it takes a lot of amount of time, especially there is a vast latency when there is a large amount of data. So then, MapD became the founding member of an initiative called OAI Initiative, which stands for GPU Open Analytics Initiative. So the idea of the initiative was to do everything on the GPUs without copying data on the CPU memory with the help of pointers, like passing the pointers in virtual RAM. So as I mentioned, MapD is a founding member along with Anaconda, previously known as Continuum, and H2O AI. So MapD has their own database on GPU. Anaconda has provided PyGDF, which is Pandas like data frame on GPUs, and H2O has their machine learning algorithms, which widely consist of linear regression, logistic regression, and generalized linear modeling on GPUs. So the good thing about this is like they all pass pointers to each other, so we don't copy data to CPU memory, and it makes analytics much faster. So a traditional machine learning pipeline, so a lot of people and a lot of processes have been included in various stages. So the one bottleneck regarding this process is like there are a lot of people, and like we use a lot of tools in a traditional data science analytics cycle, and sometimes there is a drawback, or like sometimes there is a little bit waste of time like talking to these people or using various tools. So the idea another idea and objective of GoAI initiative was to do everything on a similar platform, and we can use GPUs which have like large number of cores, and which are specifically good at some specific operations like matrix multiplication and mathematical operations, and which in turn gives us high speed. And also we are on the same platform, so we can eliminate different number of tools talking on different processes and on CPU memory. And so yeah, I can show you the notebook, but it is here on GoAI and initiative Docker, and also we have our own notebook examples on MapDML. So we have the Docker instances, so you can just download it, spin it up, and use it. I'll give you a good walkthrough. So, and we are also active on community, so please share your valuable feedback after visiting the website, and happy to raise an issue or share feedback. We'll be happy to help you. And so basically, something looks like this. This is a repository. So this is the recent project that we did with Volkswagen, using MapD and doing all analytics on GPUs, and we used XGBoost in the one specific project. So the data is masked for obvious reasons, but you can just go ahead and check it out. Like there's a whole lot of workflow which you can explore it over there. And thank you so much.
Thank you. Just want to add one thing is we recently launched our the product also in the cloud. So you can go to mapd.com/cloud and try. You can get your own GPU in the cloud with the MapD software installed. There is no credit card asked, so you should be able to just go ahead and use it for like I think 15 to 15 days free trial. And we also have we have some preloaded data sets. The taxi example that I just showed, you should be able to use that also. And then you can bring your own data set through S3. We have instructions for that. So thank you.
This is a 10-minute short talk about what one should know about Spark MLlib. So just want to make sure everybody's in the right session. Yeah? All right, so that's 10 minutes. I've never done a 10-minute talk before. So this is my first time doing this. I've given talks many times before, but never in 10 minutes. And let's see how this goes. And I also need to leave immediately after this to catch Spark to go back to San Jose. So I have to finish this by 10 minutes. Just curious, how many of you know what Spark? All right, most of you. And I guess most of you have not played with Spark MLlib component. Is that the case? All right. So we're going to learn everything there is about MLlib in 10 minutes. No, just kidding. But if you have not read this, go ahead and take 30 seconds to read it. I think it's pretty applicable to machine learning. Part of it's true, part of it is kind of funny. So just start up the file until you until the data looks right. So anyhow, very quickly at a high level, Spark is a unified data processing engine. It's very popular, being adopted by many companies, as we know. The new, not so new anymore, the data abstraction is based on the data frame APIs. Right, it sits on a very strong distributed core, Spark core level there. And just like other components are, components on top of data frames, on top of that it sits on data frame API, which is very easy to work with. So MLlib is just another component from the perspective of Spark. Okay. And the high-level goals of this MLlib component is to help make practical machine learning scalable and easy, right? To leverage the distributed nature of Spark to run all these computations in the distributed manner. So you have a large data set, like hundreds of terabytes, and you have thousands of features. You can totally leverage Spark to be able to train your model in that fashion. So it's not only scalable, but also make it easy. That has always been one of the tenets of from the Spark designers, to make things easy to use. And based on the data frame API, that's how things are a little bit easier. And also, in terms of the developing machine learning model aspect that you probably learned from the talks, usually that's involved in kind of a workflow that you go through, right? And usually you have to handcraft that, and it's kind of in the real world, it's a lot of steps you have to go through. And if you have to handcraft that, then it can be a little bit challenging to manage all that. So the MLlib also provides a few classes to help managing that, so make it easy. Okay. And to dissect what's inside the MLlib component library, essentially you can bucket those features into these 4 buckets. One of them is algorithms. Obviously, it contains a set of commonly used ML algorithms that we all know of, right? I don't have deep learning on here, but the community is actively working on integrating that into Spark MLlib component as we speak. So that's one part of the MLlib. The other one is the pipeline, which the one that I'm going to focus as the next couple slides. So I want to highlight that part of MLlib component. At the bottom, there's a bunch of facility for help with doing feature engineering, for transforming your data and whatnot, and also a bunch of utilities for doing linear algebra and generating statistics and whatnot when you work with the data. So as we know, this is a very simplified model or workflow of doing machine learning, right? We know that we got to load, clean data, feature extraction, and whatnot, and finally do model training and then evaluations, and then you might have to rinse and repeat, depends on what you're doing. So how does Spark help with this flow? Well, it provides a few abstractions that mirror pretty much each of the steps that I just talked about. So as you can see, this picture and the previous one is pretty much very similar. So we apply a transformer estimator, so those are terminology in terms of the Spark landscape, but they do what they do is pretty much the task of each of these boxes. Okay, so I'm going to go through each one of these in this block. So the first one is transformer. Transformer is commonly used for doing a pre-processing step, right, when doing featureization. Oftentimes you got to convert from your text data into numbers, or you got to transform in such a way that the input to the algorithm, because at the end of the day, everything has to be numbers. So wherever your data is, you got to transform it. You have to scale it down, scale it up. So that's what transformers are. So you can do normalize the data, tokenization, and so on. And so it does that. Once you're done with that, so you might have 5 transformers, you could have 20 transformers in your data, depends on what you're doing, and depends on what your data is. Estimator is essentially your learning algorithm, your machine learning algorithms that you want to use. That could be logistic regressions or collaborative filtering and all that stuff. So and it returns a model. With that model, we can use that to do prediction effectively. So examples here, we got logistical regression, and then that returns a model. Okay, so we have transformer, estimator. So once you have a model, you can do some predictions. The next step you definitely want to do is to do some kind of evaluation in the model to see how. That's a set of evaluators to calculate a common set of metrics, like the ORC, the RMSE, and stuff like that. So it has, like, if you do binary, then you do binary classification evaluator. If you want to use cross validator, which is a very, very cool class for helping with tuning with your parameters and whatnot. Each of these concepts, think of it as like an abstraction or an interface that has a specific method that it uses. In this case, it's the fit method. Let me go back. Estimator is the fit, and then transformer is a transform. Okay. So with transformer, estimator, evaluator, now we can build a pipeline. Okay, so pipeline is consisting of a bunch of these. In this one, it just does 2 transformer, but like I said, in your case, it could be many, many more transformer, and it can change in certain order that you want. Obviously, these things have to run in certain specific order, right? So the way you wire it up is in that specific order. Here's another example of a little messy pipeline where there are many transformers going on here, and they chain together and they work well. And, yeah, 2 of them have to complete it before we go to the next one, and so on. So how does it look in code? The code looks something like this. The first one is the tokenizer. That's a transformer. And the second one is a hashing function. That's a transformer. And then the logistic regression is your estimator. That's your algorithm. So the way you wire it up is basically create a pipeline and set the stages and give it an array of steps that you want it to execute in order. Right? And then finally, at the bottom, we have this pipeline, and we call fit on it, and give it the training data that we want to train the algorithm on, and it will automatically execute those stages in the right sequence that we tell it to do. So that's kind of the beauty behind this little abstraction to make things easier to manage. Right? Imagine you have 20 of these, then it's reading through code to see exactly what goes to what. It can be challenging, but by having this little pipeline, you can easily identify these. And the last couple slides I want to talk about is automating model tuning is very tedious work if you have done this before. There's a concept called cross-validation, using the k-fold concept by splitting the data into multiple sets, and you can run that k times. So this is k equal 5. You divide your data into 5 sections, k minus 1 for training, and the remaining 1 for testing. So MLlib provides this class called cross-validator, right? And also the param grid as well, so you can enter all the different configuration of certain parameter that you want to try to train your model on, basically. So in this example, we have 2 for the regularization parameter and 2 for link, and our flow is 3, so that means that this thing's going to run 4 times, roughly. 4 times. So you're going to get back, right? It's going to train 12 models, and then it's going to use your evaluator to figure out which one is the best one, and then give it back to us. Finally, the last slide, I got a signal back there, is the model persistence. Another cool things. You probably learned from POPs that data scientists have their own world. They do the modeling, the experimenting, whatnot. So how does Spark make it easier to hand that model over to the engineer to take to production? And the model persistence is a facility for doing that in Spark. Obviously, I think there's a lot of machine learning library out there that's trying to work with all those community to come up with a common way of persisting a model. So that's still work in progress. And 1 minute passed, and thank you. Hopefully that was useful. As you see from the title slide, I'm actually not going to talk about the past, only about the present and the future, but that's a bit, that's a trick. Could I get a quick show of hands who knows what Flink is and maybe has worked with Flink? Okay, because I'm not going to talk a lot about what that is, but I hope you still get something out of this talk. So Flink is, at the core, it is a distributed framework for data processing, and what we highlight is that it is distributed processing with stateful computations of streams. And Flink has different use cases, so it is used for batch processing, meaning data that is sitting somewhere and is static and you want to produce some results. It is used for stream processing, meaning live processing of data as it comes in, and a special case for that is event-driven applications, where you have an application sitting somewhere and you have events coming in. That might be, for example, tweets, or that might be rides happening on Uber, or that might be users using Netflix, and you want to somehow react to these events. This, in a nutshell, is what Flink is. And going a bit deeper into where Flink sits into an ecosystem, if you will. So usually you have your applications, you have your devices, you have anything that produces data. This data can then be forwarded to a data bus such as Kafka or something like Kinesis, things that we call really streaming data bus systems. It can be put into a database, or it can be put into distributed file systems or file systems. So that's where you have your data. And then Flink sits in the middle of the infrastructure, and it is basically the compute part or the processing part, and it can read from all those data sources, from streams, from files, from databases. It can emit data, like results of computations, again to streams, to applications, to S3, to Redshift, for example, to Elasticsearch, to Cassandra, Kafka, and what have you. This, in a nutshell, is what Flink is. And now I'm going to talk about some of the new features, exciting new features that will be coming up in Flink 1.5. So Flink 1.5 is happening right now. There's a release candidate out. It should be released in the next couple of weeks. And after that, I'm going to talk about some new features that we have in mind that we might want to work on. So new in Flink is a big reworking of the distributed core of Flink. So that's what we call FLIP6. So FLIP is short for Flink Improvement Proposal, and FLIP6 was a design proposal about how the distributed runtime of Flink should be reworked. And the the reasons why we want to do this rework, or what we want to achieve with that, is a tighter integration with resource managers such as Yarn, Mesos, or Kubernetes, and to enable dynamic resource management, so that Flink can go to these resource managers, dynamically request resources when it requires them, giving back resources. And also, as part of Flip6, we did rework the interface that Flink exposes to the outside world. So before there was a custom communication interface using Akka, and now there's a properly defined REST interface that users can use. So that's Flip6. Another big feature is what we call localized failure recovery. So Flink, as I said, is a stateful distributed processing system, meaning it is running on multiple machines, and these machines, they have state, and in a distributed system failures can happen, and when these failures happen, the system somehow needs to recover from that. And what Flink traditionally uses is it periodically does checkpoints to a distributed file system, and then when failure happens, it can roll back the state of all these distributed processes running on different machines to this checkpoint. But this is somewhat costly, because when a failure happens, you have to reread all that state from a distributed file system, and the localized failure recovery fixes that. So here, Flink stores some state on the machines where the computation is running, and when a failure happens, it tries to restart computations on the machines where that state is already available, and so can restart faster and doesn't have to reread state from the distributed file system. Another interesting rework is that we refactored, if you will, the network stack, so there was a 50% rewrite. This is quite low level, but what it will lead to in the end is that in streaming systems there's often a trade-off between latency and throughput. So if you want to have high throughput, you often get very bad latency, but if you want to have good latency, you often don't get good throughput. But with this rework, we think that we are pretty good at providing very good throughput and also very good latency, and improved backpressure handling. So that was kind of the low-level systems features that are new in Flink, and this is more on the API side of Flinks. So the first one is a new kind of API that we provide, or a new kind of stream, where you can broadcast a stream to multiple operations and then have state in these operations. That sounds kind of technical, but what it enables is use cases where, for example, you have a stream of data that you want to process, but you don't, before that, know what the computation you want to perform on that is. But using broadcast streams, you can and use that to process the incoming data on the mainstream. This is the use case that this enables. Another very exciting feature is the new SQL CLI. So traditionally, when you were writing Flink programs, you would have to write Java programs. So that means using the Java API that would provide data streams or for data sets, similar to how you would use the Spark API, for example. So that has a bit of boilerplate, and not everyone likes Java, and data scientists don't usually are very familiar with those kind of things. So writing SQL is something that a lot of people can do, and it's also a thing that, for example, analysis tools can generate. And Flink 1.5 has this new SQL CLI, which is an interactive command line interface where you can just input queries, and then Flink will do the rest and basically take the SQL query, generate a Flink program from that, execute it, and generate results. And one thing that makes this possible is the next point, actually, is unified table sources. So in a data processing system like Flink, you have to have a way of defining sources of data. So that's Kafka, as I mentioned, of files, and you have to have a way of defining things where you write data to. And this work that we did is about having a unified way of defining these sources. For example, when you run a SQL program, you don't want to write Java code that defines the source that you want to have, but you want to write a simple property-style configuration where you can tell Flink what the source is and where the data is coming from, what the schema is, and so on. And the last thing that I want to highlight in Flink 1.5 is something that might sound a little bit boring, but it is that we did a huge push with regards to automated testing and automated release verification, because in the past, Flink releases have sometimes been delayed because there's a lot of manual work that we're doing for each release, where we have huge checklists of things and programs that we try out and running things on the customer, which delays the release sometimes. And here we did a push of writing a lot more automated tests that we try that we can push into Flink releases. So for people that know, for example, we now have tests that use Jepsen to do failure injection and verify correctness of Flink. So that's it for the present, for the soon-to-be present with Flink 1.5 release. And for Flink versions beyond that, the stuff I'm talking about is a bit more out there, it's a bit more experimental, or we don't have yet a clear view of what we want to do, but these are kind of things that we have in our heads. So the first thing is autoscaling. So in Flink, you have your program running on a set number of machines, and when you start your program, this is the number of machines that you will have until the program finishes. So say you want to run 10 machines, that's what you're going to get. But if then you see that actually this was way too much, or this was maybe too little for the amount of data that you get, then there are ways in Flink to stop the program with the state and restart it on a different file system. But a nice thing to have would be that you can specify policies that Flink would automatically detect whether it should increase the number of resources or decrease it.